Hello, and welcome to Empowered Learning. This particular video will be about linear transformations of functions. And so in particular, what we are going to talk about in this video is how to take two functions and from that form another function by adding the two functions together, subtracting the two functions together, multiplying the two functions together, and dividing the two functions together. Okay? And so if you see here, if we let f of x and g of x be two functions, then there are other functions that can be created from these two functions. Okay, and so part of why we're studying this is to know the proper notation for basically finding a shorter way to write out the sum of two functions. So for example here, let's say we wanted to express the sum of f and g. So we would just write f plus g there as a shorthand way of notating that. So here, if we were wanting to be very specific with what the variable was, we would write it like this. And of course that means f of x plus g of x. One of the things that we need to make sure that we understand is when we see this, this does not mean f plus g times x. That does not mean that. This is just shorthand notation for the sum of the function f and g, where their corresponding variables or independent variables for the function is x. So similarly, we see that the same thing happens when we subtract two functions, multiply two functions, and divide two functions. And so, of course, whenever we're dividing, we need to make sure that our denominator right here is not equal to 0 for any value of x. If it is, then of course, that particular x value will not be in the domain of the original function. Okay. So another note that I wanted to add is that we do not write the product of f of g as f dot g of x. It's not improper to write it that way. The reason that I personally go against it is because of the use of the composition function. And so you'll probably, if you're checking out this video, then you'll probably check out the other video as well, where we will talk about the composition function and what that means. And so if you notice here that the composition function has a notation that is very, very, very close to this. And so depending upon how small you write this open circle right here to mean the composition of those two functions, then you may mistake that this is going to be the composition function and may mistake this to be the product of those two functions. And so to make it real simple, we just write it like this to imply the product, and we do the open circle to imply the composition function. And a composition function is just a function where it's made up of a function being stuffed into another. Okay? All right, so moving on. What we want to do now that we know that if we take two functions and either add them, subtract them, multiply them, or divide them together to become another function, after we form that new function, one thing that is important to us is knowing what the domain of that function is. Okay, and so that's what we're going to do in these examples here. So we have a function f of x, which is 3x plus 2, g of x, which is x divided by x plus 1, and h of x, which is cube root of x. And so we want to form the sum, the product, the difference, and the quotient of at least two of those functions. Okay, so we're going to go ahead and get started with the first example. So let's get started. So with our first function, which is f plus g of x, we know that that just means f of x plus g of x, and we know that f of x is 3x plus 2, and we know that g of x is going to be x over x plus 1. Okay, and so in looking at this, of course, we could make a common denominator here. And if we did that, that would be x plus 2 over x plus 1 plus x all over x plus 1. Because, of course, the common denominator in between 1 and x plus 1 is just x plus 1. Okay? So from here, we know that this is what this new function would look like. We could multiply this out if we wanted to. Not really necessary for what we're trying to do. But main thing here is after we have this new form of the function, we want to know what the domain of it is. Okay? And so if you recall, there are two things that we need to look out for our basic linear, polynomial, and rational functions as far as values of x that we can plug into it, meaning the domain. First thing, we do not want to plug in an x value that will make us have to divide by 0. Okay? And the second thing is we do not want to plug in an x value that will make us have a negative number under an even nth root. Okay, and so what I mean by even nth root, like a square root, fourth root, sixth root, or eighth root. Okay, so looking at this, we see that the only restriction that this particular function will have is what's going on here in the denominator with the x plus 1. And in particular, we know that x cannot be equal to -1, because if we plug in -1, we get 0 in the denominator. So from that, we know that the domain of this new function is just going to be from -infinity to -1 union from -1 to infinity, meaning that we can only plug in, the only value that we can't plug into our function is a -1. Okay? All right, so now we'll move on to our next example. All right, so for our next example, we have the function g times f of x. So we know that that's just g of x times f of x. And of course, g of x is just x over x plus 1 times f of x, which is 3x plus 2. Okay? And so, of course, we can put this over 1. And when we multiply that together, that would be like this. And of course, if we wanted to, we could distribute the x to both terms there. Not really necessary, but if we wanted to do that, we could. And so now we see that the restrictions, again, according to what we talked about before, we don't see any square roots, fourth roots, sixth roots, or anything like that. But we do see that, again, we cannot plug in a -1 right here. So the domain of this particular function will be the same as the last one, which will be from -infinity to -1 and -1 to infinity, meaning that we cannot plug in -1, but we can plug in everything else. Okay, our next set of examples here, we will have h minus g of x. And so if we look back up here, we'll remember here that our h of x is cube root of x, and our g of x is x divided by x plus 1. Okay? So again, this will be h of x minus g of x, which will be cube root of x minus x over x plus 1. For this one, if you notice, we are dealing with an nth root, but this is an odd nth root. So we can plug in any real number into this particular term. Of course, for this term here, we still have the same restriction that we had on the last two, which is that x is not equal to -1. So again, our domain ends up being the same, which is that x has to be all real numbers except for -1. Okay? Moving on to the last example, we have h of x divided by g of x. And so in this case, Our h of x again is cube root of x. Our g of x is x over x plus 1. Okay. So now when we look at this, we see that we actually have two restrictions that are going on. Okay. The first is if we look in the denominator, we know that x divided by x plus 1, this cannot equal 0. Okay. And what's going to make that equal 0 is if I plug in 0 for x right here. So all this implies that x cannot equal 0. The other restriction I have is still the same one I've had in every other problem, which is here we still know that x cannot be equal to -1, because even though x over x plus 1 is in a denominator, x plus 1 is in another denominator of itself. So we still can't have the -1 here because we still have, in this case, -1 divided by 0 as an outcome for this portion. And since that's undefined, everything else that we work with will be undefined as well. Okay? So if we go ahead and simplify this function, it will look something like this. So if we keep on going, we know that this is cube root of x over 1 times, and we're going to do the keep, change, flip principle. So we keep the numerator the same, change the operation from division to multiplication, and then we flip the bottom fraction. Okay? And so once we have that, we just have cube root of x times x plus 1 all over x. Okay? So now, looking at this, what you see here is that if you look at this function strictly in this form, you will only think that x is not allowed to be equal to 0 here. But we know by looking at it in the raw form, which is here, we notice that not only can x equal 0, it can't equal -1 either. And that is the point of doing this particular exercise, is to make sure that when we form these functions, we have to look at it in its raw form, which is this form right here, as soon as we plug in to determine what the domain is. We cannot wait until the end here to try to determine the domain, because if we do, then we'll find out that we will be misled. Okay? So with that, we know that our final answer for the domain of this function will be all values of x except for 0 and -1. So how this will look will be this way in interval notation. So we're skipping -1 and we're skipping 0. As far as what the outcome of the function looks like, the outcome of the function just looks like this. And of course, some of you may want to go in and multiply the cube root into there, into there. Not an issue with that. It's just not necessary. Okay. All right, so let's move on here. So now we have a new set of examples where we have some new functions. And so our f of x is square root of x plus 2. Our g of x is 1 over x. And our h of x is a quadratic, x squared plus 3x minus 5. And so we want to do the same things to this one. So here we know that this means f of x minus g of x, and we're going to form that function. So here this would just be square root of x plus 2 minus g of x, which is 1 over x. Okay. For the domain of this function, excuse me, I'm actually going to write that over. For the domain of this function, we have to consider the restrictions on this part and on this part, or these terms. So for the first term, we see that since we have x plus 2 in underneath the square root radical here, we know that we have to prevent this expression from being negative. So how we do that is we say that x plus 2 has to be greater than or equal to 0. And of course, if we subtract 2 from both sides, we see that x has to be greater than or equal to -2. In addition to that, we know that for our second term, we won't be allowed to plug in 0 into the denominator, because doing that will make the 1 over x term undefined. Okay, so now we have a situation where we have to meet this condition and that one at the same time. If we were to draw this on a number line, it would look something like this. So we would start at -2. We would have a bracket, and we would keep on going. But when we got to 0, we would have to skip that number and then keep on going, okay, for our x values. So if we write that in interval notation, it would look like this. So our domain would be values of x starting from -2, going all the way to 0, but skipping 0, and then moving on to infinity. All right, so for example B, we see that we have h of x divided by g of x in this case. And of course, our h of x is just our polynomial, and our g of x would be 1 over x. Okay. Now, we stop here to determine what the domain is, because this is now in the raw form of the function. Okay. And so here, if you notice, we know that 1 minus x is not allowed to be 0, but we know that 1 over x won't be 0 at any time. No value of x accomplishes that, because if we just simply divide this by 1 here, see if I can get this to work. Divide this by 1, and we cross multiply, then we get 1 times 1 is 1, and of course x times 0 is 0. So whenever we have this situation where we have something not equaling something else like that, then we know that there's no solution. Okay. On the other hand, we know that inside of here, we know that we can't allow x to be 0. And so that is a restriction. So because of that, we know our domain, again, is all values of x that are not 0. And if we now want to go and figure out what this function would look like, then we would keep the same principle here as we had before, with the keep, put that over 1, change, and then flip. And then this would look like x cubed plus 3x squared minus 5x. And of course, the difference here is that even though this looks that way, we know that we cannot plug in 0 into this function based off of how it was formed. Okay. All right, so for our last two examples, so we have g plus f of x, and then we have f times h of x. Okay. And so our g of x, again, is 1 over x. Our f of x, let's look back up here to remember what it is. It's going to be square root of x plus 2. Okay. So here we have g of x plus f of x. G of x is 1 over x. And of course, f of x is square root of x plus 2. And so again, very similar to what we had for example A here. You see example A, the only difference in between what we see for example A and B is that we're subtracting instead of adding. So for this portion, we still know that x is not allowed to be 0. And for this portion, we still know that x has to be greater than or equal to -2. So here we know the domain of this function is all values of x that are -2 or higher, but we have to skip 0. Okay. And so here, if we wanted to simplify this sum, the best that we could do is just say 1 plus x times square root of x plus 2, all that over x, okay? But really, you could just leave it in this form here. For our last example, we have f of x times h of x, okay? And so we know that for this is going to be f of x times, oops, let's fix that. So we have f of x times h of x, and our f of x is going to be square root of x plus 2 times our h of x. So let's go back up here to remember what that was. Our h of x is just a polynomial, okay? So that would be this. Now, of course, we could multiply these together, but it's better just to keep it like this. Here, the only restriction that we have is this portion right here, which we know from previous examples, x has to be greater than or equal to -2. We have no restrictions here. So, of course, our domain would just be all the x values that are greater than or equal to -2. And so that's how we would write it in interval notation. So the new function here would just be square root of x plus 2 times, and then we would write out the polynomial x squared plus 3x minus 5. And then, of course, the domain would be expressed this way. And so this concludes the video on linear transformations, how to form them, as well as define what their domain